Welcome, curious minds, to another deep dive. Today we're plunging into a question that's really been bubbling up with every new AI breakthrough. How deep does AI's understanding truly go? I mean, we've all seen the headlines, AI models just crushing competitive programming, even winning gold medals at international Olympiads. That sounds like genuine expertise, right? But, well, is it? Or are they just incredibly good at specific, maybe kind of narrower tasks? Our source for this deep dive is a groundbreaking, very recent research paper. It's titled FormulaOne, Measuring the Depth of Algorithmic Reasoning Beyond Competitive Programming. It's by researchers from AI, including Gal Beniamini, Yuval Dor, and others. Our mission today is basically to extract the most important nuggets from this paper, give you a shortcut to understanding the true frontier of AI reasoning and, what might come next. And here's the kicker. What the paper revealed pretty much right away. Even the most advanced AI models today, models like OpenAI's O3 and Google's Gemini 2.5 Pro, they utterly fail when faced with this new class of problems specifically designed to test deep algorithmic reasoning.
Yeah, it's pretty stark.
They solve less than 1% of the questions, even with, extensive help.
Less than 1%. It's a real wake-up call.
Okay, let's unpack this then, because we hear so much about these AI breakthroughs. OpenAI's O3, for example, reportedly achieving a 2,724 rating on code forces, or, securing a gold medal at the International Olympiad in informatics. I mean, that sounds like AI has truly cracked complex problem solving. It sounds incredible.
It genuinely is remarkable, yeah. And we absolutely shouldn't diminish those achievements. They're significant milestones. But what's fascinating here, and what the authors of this paper argue, is that these impressive skills, while formidable, they don't really capture the full spectrum of reasoning needed for, say, large-scale, real-world research problems.
Okay, like what sort of problems?
Well, think about optimizing global supply chains, or managing massive power grids, or designing resilient network infrastructures, these kinds of things. They're just orders of magnitude harder, requiring a kind of algorithmic insight that goes way beyond typical competitive programming questions.
Right, so different skills are needed.
Exactly. And this is precisely why the authors introduced FormulaOne. It's a new benchmark specifically designed to truly probe the depth of this algorithmic reasoning. It's built on a cornerstone of real-world optimization, dynamic programming over graphs.
Dynamic programming, DP.
Yeah, DP. Basically, it's a powerful technique for solving complex problems by breaking them down into smaller, overlapping subproblems and storing the results so you don't recalculate. Very common, very powerful. Now, this benchmark isn't just a random collection of puzzles. It sits deliberately at the intersection of graph theory, logic, and algorithms, all stuff that should be well within the training data of these frontier AI models.
So, familiar territory, theoretically.
Theoretically, yes. But the problems themselves are, as the paper says, incredibly demanding. They need a blend of, topological and geometric insight, mathematical knowledge, combinatorial thinking, and super precise implementation. The paper even gives an example of one problem needing no fewer than 15 interdependent, highly complex mathematical reasoning steps.
15 steps. Wow. Okay, so these aren't just academic exercises then? They have real-world relevance.
Oh, far from it. FormulaOne also has definite commercial interest, directly relating to practical, large-scale optimization challenges. Think routing, scheduling, that sort of thing. And what's maybe even more powerful for future AI development is how it's generated. It uses a framework called Monadic Second-Order logic on graphs, MSO logic.
MSO logic.
Yeah, it's a powerful formal language. Think of it almost like a blueprint that lets researchers automatically generate a basically endless supply of these incredibly complex graph problems.
Ah, so it's scalable for training.
Exactly. Ideal for building next-generation reinforcement learning environments, especially those with verifiable rewards. And crucially, many problems in FormulaOne are intimately related to the actual frontier of theoretical computer science, specifically to central conjectures like the strong exponential time hypothesis, or SETH. We might come back to that.
Okay. And as you mentioned earlier, the results when they tested the state-of-the-art models were, pretty startling.
Absolutely humbling is the word I'd use. The results the paper found are a really sobering reality check. Top models like OpenAI's O3, O3 Pro, Google's Gemini 2.5 Pro, and even xAI's Grok 4 Heavy, they failed dramatically on FormulaOne.
How dramatically?
Less than 1% solved, even when given 10 attempts and explanatory few-shot examples to guide them.
So even with hints, basically?
Even with hints. And Grok 4 Heavy specifically solved exactly 0%. Nothing.
Wow, less than 1%. 0%. That's truly humbling, especially given their other achievements. So AI hits a wall here.
Yeah.
But the why is the fascinating part, isn't it? What makes FormulaOne so fundamentally different? What does this failure really tell us about AI's expertise?
That's the million-dollar question, right? What exactly is this deep algorithmic reasoning, and why do these problems totally stump the AI? Well, it seems to boil down to the complexities of dynamic programming, DP, particularly on what are called tree-like graphs.
Tree-like graphs.
Yeah. So imagine a complex graph being broken down, sort of decomposed, into a tree decomposition. Picture a collection of small sets of vertices, they call these bags in the paper, and these bags are organized into a tree structure.
Okay, like a hierarchy of small pieces.
Kind of, yeah. Think of it as a roadmap for an algorithm to process the whole graph. You traverse this tree of bags, and each bag acts like a local window into the bigger problem. There's a measure called tree width, which captures how tree-like a graph is, how complex this decomposition needs to be. And the difficulty of the problem is intrinsically tied to the size of this window, the size of the bags.
Okay, so it's about navigating this complex roadmap, this tree of bags, and keeping track of everything as you go.
Precisely. Solutions for these kinds of problems involve traversing this tree, moving from bag to bag, and building up partial solutions along the way. The real art here, the tricky part, is designing the state. The state is the minimal information you need to summarize a partial solutions interaction with the current bag you're looking at. It has to be rich enough so you can update it correctly as you move to the next bag in the tree, but it also has to be concise enough so the whole thing doesn't become computationally impossible.
A balancing act.
A very delicate one. And even a seemingly simple classical problem like dominating set, where you're just finding the smallest set of vertices that dominates all others, even that requires incredibly precise tracking. You need to know if a vertex is in the set, out-dominated, or out-needs domination, and how these statuses interact. This level of granular interdependent state management over a complex structure, that seems to be where current AIs often falter.
Okay, so they struggle with keeping track of all the details and how they connect.
That seems to be a big part of it. The paper highlights a series of subtle but really critical errors these AIs made, even though the problems were, algorithmic challenges. Theoretically, their home turf. For example, they often fall into traps like premature invalidation. It means they'll discard a potential solution way too early because it looks disconnected within the current bag or window they're examining. They fail to anticipate how information revealed later in other bags down the tree might actually connect those pieces and make the solution valid after all.
Ah, so they're too focused on the local view. They lack foresight.
It points to something like that, yeah. A difficulty in holding multiple possibilities in mind, or maybe a lack of true long-range planning within the algorithm's execution. Another common pitfall they found is this failure to cap solution cardinality.
Cardinality.
Like size.
Exactly. For some problems, once you reach a certain number of vertices in your solution, say K4, the exact count beyond that doesn't matter anymore. You just need to know it's at least 4.
Yeah.
But the models often fail to recognize this. They keep meticulously tracking the exact count, 5, 6, 7, leading to what we call a state space explosion.
Meaning the calculation just blows up. Right. It turns what should be a manageable, maybe linear time computation into something cubic or worse, basically impossible. It's like they're, counting every single leaf on a huge tree when all they need to know is whether the tree has enough leaves. They miss the abstraction.
And missing the forest for the trees, literally.
Pretty much. They also struggle with things like tracking external connected components.
Mm-hmm.
Sometimes they overlook just a single critical bit of information, like one flag that indicates if a valid connected piece of the solution has sort of detached from the current bag's view. This tiny oversight can lead to disqualifying perfectly good solutions or incorrectly merging components later on.
Wow, these are subtle errors.
Very subtle, but fatal for the solution. Then there are tricky issues with avoiding double counting when you merge partial solutions from two branches of the tree, especially when vertices are shared between bags. And also the need for really careful merging of connectivity partitions, often requiring sophisticated data structures like disjoint set union or DSU. Getting the logic slightly wrong there messes everything up.
So it sounds like a fundamental difficulty with abstraction, managing complex dependencies over time, and handling how things connect and change.
I think that's a good way to put it. And sometimes the challenge is even figuring out how to represent the state effectively in the first place. Take the cograph problem they discuss. It involves finding subgraphs that don't contain an induced path of length 3, basically. No line of 4 vertices where only adjacent ones are connected.
Okay.
Solving this with DP on a tree decomposition illustrates what the authors call geometric complexity in state representation. It requires the model to track really intricate details about pairs of vertices and even their forgotten neighbors' vertices that were in previous bags but aren't in the current one.
That sounds incredibly complex to keep track of.
It is. It shows that AI struggles with abstracting and dynamically updating these complex spatial and structural relationships. It's not just about counting or simple pattern matching. It's about understanding evolving structure.
And I heard you mention earlier there's a fascinating mathematical trick involved in one of these problems, something that really highlights the gap.
Ah, yes. This is where it gets really interesting, and it beautifully shows the value of genuine mathematical insight versus just crunching through possibilities. So imagine you combine two problems, the cograph problem we just mentioned and the standard bipartite graph problem, checking if a graph can be colored with two colors.
Okay, two problems combined.
A purely mechanistic AI, or maybe just a naive approach, might try to combine the complex state representations for both problems. That would lead to an absolutely enormous, probably unmanageable state.
Right. Sounds computationally explosive again.
Exactly. But, and this is the brilliant part the paper points out, there's a critical mathematical lemma, a known theorem. A cograph is bipartite if and only if it is triangle-free.
Wait, that's it. Just check for triangles. That simplifies it massively.
Precisely. If you know that piece of mathematics, the problem becomes vastly simpler. Instead of tracking all the complex bipartite properties and cograph properties, you just need to ensure that no bag in your tree decomposition introduces a triangle. Recognizing this insight, which apparently current AI models really struggle with, fundamentally reduces the problem's complexity. It's a huge shortcut provided by mathematical abstraction.
So the AI can execute complex procedures, but isn't making these conceptual leaps based on underlying mathematical truths.
That seems to be the crux of it. They can follow recipes, even very complex ones, but they aren't yet discovering the fundamental mathematical principles that allow for elegant simplifications. They can crunch the numbers, but they're not yet, understanding the math in that deep sense.
Okay, so if FormulaOne is exposing these really deep limits in current AI, what does this mean for the future? For AI development, and maybe even for our understanding of theoretical computer science itself.
Right, connecting this to the bigger picture. FormulaOne isn't just, another benchmark to add to the pile. The authors see it as a strategic move forward for AI research. They contrast it with something like the ARC benchmark, the abstraction and reasoning corpus. ARC tests out-of-distribution reasoning, basically. Can AI handle problems truly unlike anything it's seen in training?
Okay, testing generalization to the unknown.
Exactly. FormulaOne, though, is different. It challenges AI within its known training distribution. Algorithmic coding problems, graph problems. This is supposed to be AI's bread and butter, especially for models trained on code. The failure here is particularly significant because it shows these models can't perform deep multi-step reasoning, even in supposedly familiar territory.
So it's not about lacking exposure to the concepts.
It doesn't seem to be. It suggests a fundamental gap, not in the breadth of knowledge, but in the depth of understanding and the ability to synthesize nuanced information across many interconnected steps.
Right. It's not about what they know, but how deeply they can reason with what they know. That feels like a really crucial distinction.
Precisely. And this limitation has big implications for fueling future AI research. Because FormulaOne is built on that MSO logic framework we talked about, it provides an essentially unbounded source of high-depth algorithmic challenges.
An endless supply of hard problems.
Exactly. And this is ideal, as the paper puts it, for building next-generation environments for reinforcement learning with verifiable rewards, or RLVR.
Why is that combination, hard problems and verifiable rewards, so important?
Well, the issue with many existing RLVR benchmarks is that they often have fairly low conceptual depth, or they're static, a fixed set of problems. FormulaOne offers something different, a virtually infinite stream of problems with profound mathematical depth, but crucially, problems for which the solutions are nevertheless automatically verifiable because they're generated from logic.
So you get endless novelty and depth, but you can still tell if the AI got the right answer.
Exactly. And that combination is seen as critical for training agents to tackle genuinely open-ended scientific discovery, where problems are hard and you need reliable feedback. And finally, getting back to that theoretical computer science angle, it has potentially profound implications for pushing the boundaries of complexity theory itself.
How so?
Remember the strong exponential time hypothesis, Seth, that we mentioned?
Vaguely, yeah. It relates to how fast certain problems can be solved.
Right. It basically posits that certain fundamental problems, like finding satisfying assignments for logical formulas, SAT, require exponential time, and you can't do much better. Now, the time complexity, how long it takes to solve them, of many core graph problems, including several in the FormulaOne dataset, is believed to be optimal, assuming SETH is true. They're thought to be inherently hard.
Okay, so where does AI come in?
Well, what's fascinating here is the possibility, maybe a long shot now, but still, that if a powerful AI agent, perhaps trained on something like FormulaOne, were able to discover a genuinely novel, faster algorithm for one of these hard tasks,
It wouldn't just be solving a puzzle.
it would effectively refute a central hypothesis in theoretical computer science. It would prove SETH wrong, or at least show that our understanding of the complexity of these problems is incomplete.
Wow. So AI could actually make fundamental discoveries in theoretical math and computer science.
That's the potential implication, yes. It could genuinely push at the frontiers of complexity theory, leading to profound theoretical breakthroughs, not just practical applications.
Okay, so let's try and summarize our deep dive today. It seems like while AI has made truly incredible strides in many areas, like those impressive ratings in competitive programming,
Yeah, definitely impressive.
this FormulaOne benchmark highlights a pretty fundamental gap, a gap in AI's ability to perform the kind of deep, multi-step algorithmic and combinatorial reasoning that's needed for really complex real-world problems, and even theoretical ones.
That sums it up well.
It's not really about the sheer breadth of knowledge AI possesses anymore. It seems to be about the depth of understanding. It's about the ability to synthesize nuanced information, make those conceptual leaps like the triangle insight, and manage complex interdependent states over many steps.
Exactly. Those are the skills that seem to differentiate, true human expertise from what even the most advanced AI can currently achieve in this domain.
It really puts AI's expertise into a different kind of perspective, doesn't it? So, this leaves us, and you, the listener, with a final thought to mull over. Given that AI currently struggles with these deep interconnected reasoning steps, the very skills we often associate with human ingenuity and innovative problem solving, what specific areas of human expertise do you think will remain uniquely human for the foreseeable future? And maybe more importantly, why? What is it about those skills that makes them so hard to replicate?